So this is part 3 of section 6.6, dealing with number theory. So next we're going to talk about Euclid's procedure for generating a perfect number. So the ancient Greeks knew the first 4 perfect numbers were 6, 28, 496, and 8128. In fact, one of the propositions from the 4th volume of Euclid's Elements states that the procedure that uses Mersenne primes to find a perfect number. So Euclid's procedure is that if n and 2 to the n minus 1 are both prime, then 2 to the n minus 1 times 2 to the n minus 1 is a perfect number. Okay, so note here, in this first part of our product, the n minus 1, that whole thing's in the exponent, and then in the second one it's just n and the minus 1's outside after we take the exponent. The processing matters here. Okay, so we're going to go ahead and use this, and we're going to practice it to show you what it looks like with n equals 2, n equals 5, and n equals 7. You're going to do n equals 3 on your own and then check it in the PowerPoint that comes with this, just for the sake of time. So let's do n equals 2. Okay, so when we do n equals 2, we have to find this piece and this piece, multiply them together, figure out the proper factors, and then we make sure it's the perfect number. Okay, so we're doing the whole shebang. So first we do 2 to the 2 minus 1. So again, here 2 minus 1 is in the exponent. This becomes 2 to the 1, so now our exponent's 1. Anything to the first power is itself, so we just get 2. And then when we're trying to find the other piece, 2 to the n minus 1 would be 2 to the 2 minus 1. So that'd be 4 minus 1, so that's a 3. So again, these are different numbers. Okay, so be careful with your notation. Careful with your notation. So then when we multiply them together, 2 to the 1 times 2 to the 2 minus 1 would give us 2 times 3. So we get 6. And then to figure out if it's proper, or sorry, if it's perfect, we take our proper factors and we multiply them together. 6 we found earlier, so the proper factors are 1, 2, and 3. So when we take that sum, we get 6, which is perfect because it's equal. Okay, so 6, one of Euclid's perfect numbers. All right, let's try it again with 5. N equals 5. So I'm gonna find the 2 pieces first, multiply them together, and then take the proper factors just like we did before. So 2 to the 5th minus 1 would be 2 to the 4th, which is 16. 2 to the 5th minus 1, we already found that earlier, that's 31. So then when we multiply them together, on the calculator, minus 1 is 31, just like we said. We're going to multiply that by 2 to the 4th. So we get 496. So now we have to go through the factors of 496. Okay, so first thing we're going to do, we're going to find the square root of 496. And that's 22.27. So that means it's going to fall between 22 and 23. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So then we're done. So we're just going to run through them all. So we have 1 and 496, 2 and 248. When we figure out if it's divisible by 3, we do 4 plus 9 plus 6. Remember, we used that sum. We learned that last section. We got 19. 19 is not divisible by 3, so that means 3 is out, and anything divisible by a multiple of 3 would be out. So that means 6, 9, 12, 15, 18, and 21 are all out because 3 is out. Okay, so then we try 4. 496 divided by 4, and we get 124. Okay. For 5, the divisibility rules had to end in a 5 or 0. It doesn't, so that means 5 and any multiple of 5 is out. So 5, 10, 15, and 20 are out because 5 is out. Right, so that means the next one we have to check is 7. 7 doesn't work because we get a decimal, so 7's out. So that means 14's out and 21's out. Okay, so then we try 8. We get 62. Okay, then we try 11. 11's out, so that means 22 is out. Okay, so our list is getting smaller. Try 13. 38 point something, so that's out. Try 16. 16 should work because we got it up here, so it should give us 31. Let's try 17. 17, we get 29 point something, so 17's out. Let's try 19. 19, we get 26 point something, so 19's out. So then our proper factors are going to be 1, 2, 248, 124, 8, 62, and 16, and 31. Okay, so again, we're not including 496 because 496 is not considered to be a proper divisor. So when we add all of these up, I'm just going to do my calculator. We get 492. Oh, I missed 4. That's why. Okay, so the sum is still 496, so it is perfect. And we do a happy face because that's the answer we should have gotten, and we're excited. So 496 is a perfect number. Okay, so now we're going to try n equals 7. So I'm going to leave a pause here so you can pause it and catch up, or try 7 on your own, and then we'll run through it. Alright, so let's do n equals 7. So we go 2 to the 7th minus 1. So again, 7 minus 1 is in the exponent. So we get 2 to the 6th. 2 to the 6th is 64. Okay, then we have to do our 2 to the 7 and then subtract 1. So 2 to the 7th gives us 128. So we get 127. So we multiply these together, so 2 to the 6 times 2 to the 7 minus 1 would be 8,128. And this one's rather large. We're not going to check all the factors. I'll leave you guys to do that on your own here. So what we're going to do instead is just do the square root, just to give you a ballpark of what you would need to do. So the square root is about 90.2. Okay, so taking a look at this one, I found all the proper divisors. So again, you can do that on your own. Sorry, the proper factors. And that was 1, 2, 4, 8, 16, 32, 64, 127, 254, 508, 1016, 2032, 4064. When I summed them all up, I got the same, so it's a perfect number. But again, we're looking here at the formatting. So what we really want to write, because we're trying to see if 2 to the 6th times 2 to the 7th minus 1 is perfect, and it is. So we'd say that is perfect. And we could rewrite that for all 3 of these. So here we do 2 to the 1st times 2 squared minus 1 is perfect, because again, that's the form we're testing. And then here would be 2 to the 4th times 2 to the 5th minus 1. So again, you can check 3 on your own. That one's a lot smaller, so it's a little bit nicer. So there's one more piece that we just want to touch on this. So here we're told that 2 to the 31 minus 1 is prime. Now this one we can't do in our calculator, because if we try to do even just 2 to the 31 on your calculator, so I'm just going to show you that quick. 2 to the 31 power, it's very large. And I don't want to multiply that by anything, so we're just going to leave it as 2 to the 31 just because it's so large. So if this is a Mersenne prime, that means that it's associated perfect number, right? So here this means our n is 31, and remember that's prime. That was part of the stipulation of this process. So that would mean that our 2 to the 31 minus 1 would be 2 to the 30. So again, another really large number. We're going to leave that alone. So then our perfect number the associated perfect number is 2 to the 30 times 2 to the 31 minus 1. So that would be our perfect number. And again, you could try to calculate that, but not every calculator is going to be able to handle something that large. So you don't have to calculate it. You can just leave it. And this time, with such a large exponent, you want to leave it just as it is. So that would just be the associated perfect number. And again, with this one, we're not showing that it's perfect. We're just touching on it.